In 9a, we're supposed to figure out the smallest possible degree of each function. In 9a, what I first want to do is I'm going to look at my end behavior. I know that it has opposite end behavior by the shape of the graph. This one's going to positive infinity, that's negative infinity, so that means it must be an odd function. I'm also going to look at the number of zeros it has to help me out. It has 1, 2, 3 zeros. So because it has 3 zeros, it could be at least a third degree polynomial. But what's going to keep it from being a third degree polynomial is the fact that it has 1, 2, 3, 4 turning points. If it has 4 turning points, then it has to be at least a fifth degree polynomial. A third degree polynomial has a maximum of 2 turning points, but a fifth degree could have as many as 4, so that would fit the bill. This is a fifth degree polynomial. In our second equation, the first thing I notice about the second equation is its end behavior. The end behavior of this one is the same. So anytime it has the same end behavior, or you could use the shape of the graph, if it's U-shape, it has to be even. It only has 2, and there's zeros on here that we can locate. They're close to where I hit those dots. So there are zeros, and I was just writing that in there. There are only 2, so that would tell us it's at least a second degree polynomial. And then we have to count our turning points to help us from there. It has 1, 2, 3, 4, 5. Okay, so it has 5 turning points. If it has 5 turning points, that means it has to be at least a sixth degree polynomial. Right? Because if it's a fourth degree, it could have at most 3. If it's a second degree, it has to have at most 1. So we got to bump up and get past that 5 degree or fifth turning point, which means it's a sixth degree polynomial. So use your clues of turning points and zeros and the end behavior to help you figure out odd, even, and then the degree of the polynomial.